In this tutorial, we will learn about the structure of output files that Petrolog saves for the case of a simple calculation where the starting composition has only major elements, those you can see here on the screen, but no trace or volatile elements, so everything in here is zero. Before watching this tutorial, it is recommended that you watch another tutorial on saving results of calculations to files. So I have here a simple case where we have three different minerals crystallizing, and also note that I have pure fractional crystallization conditions set here. So percent of fractionation is 100 for each mineral. And before we start calculation, I'll just unclick to follow output on the screen so we can have a look at what's being reported during calculations. So as you can see in this section, in the define output frequency, we will report results every 1% of crystallization. So let's click start, and at the start you will see the calculation parameters we selected and then the results of calculations as they proceed. When Petrolog shows the results of calculations, you have the composition of the magma, you have the composition of the melt at the magma, composition of the minerals which are currently forming, and if the minerals are fractionated, also the compositions of the cumulate and minerals in the cumulate. So this is the very start of crystallization. We've just formed the first mineral. You can see that the amount of mineral form is 0.01% and 99.99% of the melt remaining, and this mineral has been placed in the cumulate. So if you look at the amount of phases in the magma, it is only melt. When crystallization proceeds, olivine keeps forming from the melt, and all the crystals are being formed into the cumulate. So now we have already 1% of olivine crystals formed. This is the composition of the olivine as it is being formed, but as soon as it is formed, it's placed in the cumulate. So here we have 2% of crystallization already completed, and if you notice here, the composition of the olivine which is forming is now different from the composition of the bulk olivine in the cumulate. It's because this is the instant composition of olivine, and this is the bulk composition of olivine which has been formed so far. As crystallization proceeds, eventually plagioclase will start forming, and again it will be going straight into the cumulate. So now the composition of the cumulate is a sum of the olivine and plagioclase crystals formed. Again, in the magma we only have melt. All crystals are separated from the magma and they're sitting in the cumulate. And if we keep going towards the end, we will see that clinopyroxene will eventually join the calculation. So here you can see it's already clinopyroxene. Three minerals are crystallizing from the melt, and again all of them are in the cumulate. So the combined composition of the cumulate is shown here, and these are the bulk composition of all three different minerals in the cumulate. And because there is only melt in the magma, the composition of the magma and the melt are the same all the way through, and then we eventually reach the end when we reach 20% of crystallization. So let's import these results into Excel and examine the structure of the output files. So the Excel file now has 5 different sheets. The first sheet is for the calculation parameters. So everything which was defined before we start calculations is written here, and you can examine it, including the version of Petrolog which was used for those calculations. The next sheet is the largest sheet in the output file, as it contains lots of different information. The first set of columns here are the composition of the magma. These, in this case, from A to M. The next set of columns is the composition of the melt. As we mentioned, for this particular case, the melt and magma has exactly the same composition. And then these columns are followed by the columns with the composition of the cumulate. And as you can see here, the composition of the cumulate is changing as crystallization proceeds. So each row in this file corresponds to the intermediate state of the system at the set frequency of the output, and in our case it was 1%. So each 1% we have new output line added to the file. These three sets of columns with compositions are followed by the columns with temperature. The first column is the accepted temperature of the melt, and the next three columns in this case are the pseudo-liquidus temperatures calculated for each of the minerals that are taking part in calculations. Towards the end, if you remember, three minerals were crystallizing, and what this means that these three pseudo-liquidus temperatures are effectively the same, which means that they're all crystallizing together. At the beginning, you would note that olivine temperature is much higher than plagioclase and clinopyroxene temperature, which means that only olivine is on the liquidus of the melt, and then eventually olivine and plagioclase temperatures are the same, so that's when the plagioclase joined the calculation, and as we already said, later on clinopyroxene joins calculation. So these columns here are showing the accepted temperature and the pseudo-liquidus temperatures as crystallization proceeds. These columns are followed by a set of columns that provide the compositional parameters of the minerals that are forming. -1 means that this mineral is not crystallizing. So here is the forsterite of the olivine, which is forming an equilibrium with the melt, and you can see the forsterite is decreasing as crystallization proceeds. For olivine, we also provide olivine melt distribution coefficient, Kd. Then this is followed by anorthite for the plagioclase, and you can see that plagioclase has joined crystallization later than olivine, and then there is Mg number of clinopyroxene in the magma. So these are the compositions which were in equilibrium with the melt as crystallization proceeded, and then the next set of columns are showing the compositions of the parameters of the bulk phases in the cumulate. And as you would note, that these are different from the compositions of, let's say, olivine in equilibrium with the melt, because these are combined composition of all olivines which were formed so far, and they are always more magnesium than the composition which is currently forming. The same is true for plagioclase. Plagioclase in the cumulate, combined plagioclase in the cumulate, is always more calcic than the currently crystallizing plagioclase. These columns are followed by the pressure, and in this case we use constant pressure of 5 kilobars. Then there is oxygen fugacity and how it is different from QFM, then density and viscosity of the melt, and towards the end are phase proportions. So the first column is the percentage of melt in the magma, because in this case we have chosen to do pure fractional crystallization. There are no minerals in the magma, so all these numbers are 0. And our crystals are in the cumulate, so these columns here are showing us the percentages of phases in the cumulate. So the total amount of crystallization, as you'll see, is 20%, and the combined is obviously 100. As you can see at the bottom, their sum is 100. So we have 8% of the melt and 20% combined crystals. Now, if we have a look at the output we had on the screen, in addition to the composition of cumulate, which we've seen with you in the output file, we also saw the compositions of bulk minerals in the cumulate. With the default settings for producing output files, these are not recorded in the output files. What's recorded in the output files is the compositions of minerals which are in equilibrium with the melt. So minerals which are forming in each step of crystallization, and these minerals are, their compositions are recorded in those separate files here. So these are the compositions of plagioclase which formed during crystallization in equilibrium with the melt, and the extent of fractionation is shown in that melt fractionation column here. The same is true for olivine. Again, exactly the same type of information provided for olivine, and obviously the same type of information is provided for clinopyroxene. Now you've noticed that there is different number of rows for each of the files, and that's because they joined crystallization at different stages of evolution. So the first clinopyroxene appeared when there was approximately 86% of the melt left, 14% crystallization. The first plagioclase occurred when there was approximately 4% of crystallization, and the olivine obviously crystallized from the very beginning. Now, if we would like also to add the compositions of the bulk mineral phases in the cumulate to the output files, we can do this, and to do that we need to go into Tools Options and click on that Add Export of Cumulus Phases to Files. You would also note that there is another option, Add Export of Elemental Concentrations to Files. This is probably not really beneficial for simple compositions as these ones, but I would add this option as well so that we can examine the difference between the results. So now let's repeat the calculation results with those new options chosen, and I draw your attention to this part here, as these results will be overwritten. Please watch the number of files which will be formed now as we click Start Calculations. As you can see, there are many more files now appearing in here, and that's because we are additionally saving cumulates, and we are saving the compositions as elemental concentration, not just as oxides. So let's now export these results to Excel. And you will see there is now a larger number of different sheets. So the first sheet is the same. Now there is a sheet which shows all the compositions now of the magma and melt in elemental concentrations. And now you note that there is also a column of oxygen which shows you the total amount of oxygen in that composition. It is for the magma, it is for the melt, and it is for the cumulate. If we go to the file which was also present in the original calculation we did, you will see that the oxygen column has 0 in there, and that's because all oxygen is distributed between those major elements forming oxides. Now exactly the same situation is for the plagioclase. So this is plagioclase in the magma, same file we had before, but now these compositions are also shown as elemental concentration with a separate column for oxygen present. In addition to plagioclase in the magma, we also now have plagioclase in the cumulate. So these are the bulk compositions of plagioclase as crystallization proceeded, as they are in the cumulate. So to remind you once again, if we are going to the main output file, the bulk composition of the cumulate is here, including all phases in the cumulate. The compositional parameters of minerals in the cumulate are presented also in this file here, but the actual compositions of the minerals, if you check that option for exporting them, are exported in this file. So this is the composition of the minerals in the cumulate, and exactly the same is true obviously for all other minerals. So here you would have many more sheets in the Excel file, and it will provide you many more information if this information you require. So this completes the first tutorial on the structure of the output files. This tutorial is followed by another one where we consider a more complex case, where you also have trace elements present in the starting composition.